Hello, this is Dr. Satish Singhal, PhD, Professor of Computer Science, El Camino College, Torrance, California. This is third video of the series of user-defined functions. Interestingly enough, in this one, I would like to talk about pointers because one very important application of user-defined functions requires at least a reasonable knowledge of pointers. Later on, pointers will be used in more details for building large structure like linked list which can make very good use of fragmented memory and can store a lot of data in rather small non-contiguous spaces. Okay, once again, there is disclaimer: video is not done professionally. There might be speech errors because I'm not working with the script. You should read relevant chapters from any textbook on C or my ebook, and only then video will help. The video cannot be your first exposure to the topic. It should be, if it is first exposure, you'll have to go and read books and other things or take a course. This is not a replacement for taking courses, not having books and things like that. Okay, so when there is a software need to pass large blocks of memory to a user-defined function, that's where user pointers become very important. We learned in part 1 and part 2 of this video series about passing parameter to functions using pass by value, or which is passed by copy mechanism. And in this mechanism, a copy of data passed to the function is made into the parameter passed to the function. Therefore, during the function invocation, two copies of the same data exist. That's pass by value or pass by copy mechanism. Pass by value can work without any memory overhead when data passed to function is a small block of memory. Int is 4 bytes, double is 8 bytes, character is 1 byte. If you're passing these small pieces of data, that's not a problem in passing by value. But when we need to pass large blocks of memory to user-defined function, this mechanism, pass by value or pass by copy, completely fails because it becomes memory hogger, because for the time during which function is being executed, two copies of the same data exist. And if data being passed is huge in number of bytes, hey, that's a tremendous memory overhead. And certainly in today's mobile devices, which have limited battery life, that can be a huge battery killer as well. Okay, question you're going to ask me: when do we need to pass large blocks of memory to a function? Well, there are a couple of examples. When we need to print a large block of text and it is passed to the print function, let's say a printing press wants to pass print Bible. Well, there would be a function print that'll send it to the printer, and you could do it page by page, but that's software wise, that's very inefficient. They may want to pass entire text to the print function at once, which will send it to the printer. Well, if you pass by value, during that time, the data source and the print function will have copy of the Bible in the RAM, which is huge memory hogger. Okay. Second situation is that later on we'll learn something about structured records, which are composite data type with no upper limit in number of variables they can contain. Passing them to a function is also an example of passing large blocks of memory. Or we can pass to functions large lists like arrays, linked list, and binary search tree. These are all large blocks of memory that could be passed to a function. Those are some of the examples. And each one will be a huge memory hogger if it was passed by value, passed by copy. So it is clear that for software to be efficient, we need to discover another mechanism of passing data to function, which will not increase memory overhead, or, to be blunt, not kill batteries in mobile devices. This mechanism should be such that we do not copy data to the user-defined function into function argument. Rather, we just copy the first byte of the address of the large block of memory that user-defined function is going to use. And then function can have access to the rest of the large block of memory because it has the first byte of the memory passed to it. And this is conveniently done by using a C variable type called pointers. Pointers can actually store address of variables or blocks of memory that has a name. So if you have a string that has a name, if you have Bible stored in a string that has a name, if you have an array, linked list, those have a name. Okay, so people are scared of pointers, so we are going to introduce them rather gently. First, we would like to talk about address of variables, constants, and functions. All have address. Every entity you code in your program has an address. And after familiarizing ourselves with the address of variables, we would like to learn the ways to store variable addresses and actually see as a facility for them. General name for this technology is pointers and their use. And now it's not that you have not used pointers so far, you actually have. Why do you think that we pass address of a variable to scanf when we take user input? That is because scanf takes a pointer to the data store variable as an argument. Here's the example. Scanf makes use of pointers. Look at the header of scanf from c++.com. This is actually a brief header. So it has a first argument as const char point. This means pointer, not multiplication. I'm going to emphasize that several times. This is not multiplication sign. This is just a meaning that char asterisk is a data type, which is pointer. So first argument is the format string. Second is int asterisk storage variable. So what that means is that notice asterisk after the word int. Taken together, int asterisk means that variable after int asterisk, which is this one, can store address of a data that is int type. And soon we'll see more on the asterisk and pointer variable using it. One more time, note that this asterisk has nothing to do with binary multiplication operator. Okay, so scanf already used pointers, that's why you're passing. If you're taking input for an int, here will be the format string, which is quotes %d, and then here you'll put the address of variable where you want data to be stored. That means this variable, storage variable, can store address of an integer variable. Okay, so we get back to the topic of every variable having an address. All program variables, constant and even function names have address in memory. In other words, our RAM is an addressable memory. Like every house in the US has a number, every block of memory has an address. These addresses can be printed out simply by using the address of or ampersand operator. We will show that to you very shortly. And in this video, I'll be using word variable generic sense. I'm going to be using it for variable, constant, and function names. And this next slide shows the example. So here's the example. Let's say I have a variable num minus 10 and I want to print its address, means memory location where is. I want to print memory location of its first byte where it's stored. So we can do something like this. Printf %p for the pointer /n, that's for line feed, ampersand num. And if you do that, address will be printed in hexadecimal, and operating system simply guarantees to you that when this variable is created, an address will be assigned. It doesn't guarantee where it will be assigned. In each invocation, it may end up at a different memory location. Since every variable, constant, etc. will have an address, sometimes we can make use of address of a variable. I would like to show those things to you in compiler Xcode and put concept of pointers in somewhat firmer background. So let's go to Xcode now here. Okay, so font may be a little small here, but hopefully you can see it. I do pretty much what I did in the PowerPoint. I create a variable called num, and here you are pretty familiar that if I do code like this, it'll print the value of num, which will be -10. And I have already run it. You'll see that my first output is -10. Okay, and then I want to print address where num is stored. Format string to print address is %p. However, that gives address in the hexadecimal form, and this line 18 is printing the address of RAM, address of num in RAM, in hexadecimal, of course. There's a more syntactically strict version of this later. We'll expose that later. But interestingly enough, I printed value of num here with the name of num, but we can print value of num in another novel way. This novel way has to do with the fact that because address of num is storing address of num, ampersand num is storing address of num, can we use this information to get access to num? And indeed we can. That is, we put an asterisk before address of num in parentheses. Okay, like this. I'm going to comment this out for a minute and I'll bring it back. So if we do that, notice that this line 25, num value printed indirectly using its address, num value printed indirectly using its address came out 10 -10 also. Notice the syntax here. This means that this whole thing really means that I got access to the num, first providing its address and then using this asterisk operator. By the way, if you are bothered by this, you can print address in non-hexadecimal form. I've done that right here, and if we do that, we'll get the non-hex form of the address, which is very long numbers. That's why hexadecimal was designed, so you can get it in short form. Okay. All right. So address of num, asterisk in front, gives us the num itself. So it would appear that asterisk operator gives access to variable at certain address indirectly. Okay, we got access to num indirectly by putting the asterisk in the front and the address. Since we got access indirectly, we also call this process indirection. And it has another name called dereferencing. And that name came because ampersand makes reference to memory location. Dereferencing means that we are getting access to the content of that memory location. Okay, so this is very important that you understand that once there is an address here, whether it's stored in a pointer or directly, if you put asterisk in front of that, that means indirectly we are getting access to that variable. Okay. Now it is interesting that using this technology here, we can change the value stored at num. We can change values stored at num directly if we set num to something else, but we can change it using this syntax also. Meaning of that is, go to this address where num is stored, grab hold of that variable and put 22 in it. Here we had read access to the variable num through its address, and using indirection on that, using dereferencing on that. Here we are changing it to new value. And you will be surprised that if I print with name num and we print by dereferencing or doing indirection on the address, this num and this, they'll give same value, which it did, 22 and 22. Okay. And this is strict version I was talking about was C specification required that you print address stored in a pointer or address of variable this way. But that's a minor issue. We're not going to worry about that too much. Okay, so remember two things. That when you put ampersand, we print the address. When we have ampersand and variable name and put asterisk in the front, we print the content. If somehow this could be pointer, then also we can print content through the pointer, and that can be done. And we can change the value also by this syntax where address is there and then we are dereferencing that address. And if this were a pointer, we could do the same thing. Now we're going to show some of these things which, if your mind is buzzing now that okay, there's so many different syntaxes, we're going to make things very simple very quickly. Let's go to PowerPoint again. Okay. So we did this num minus 10, but we can, in RAM Cloud, this declaration will look like this, that there is a variable called num, has minus 10. Its first byte starts at 1004. If it's 4 byte, last byte will start at 1008. Okay. These are fictitious memory addresses. Real addresses are assigned when program is run. Okay. Imagine that this is the syntax of declaring pointer, by the way. Int asterisk ptr. Meaning of that is that this can store address of an int type variable. Now I understand some of you are kind of saying, okay, God, I mean, here I had just one token to declare a variable. All of a sudden, I'm supposed to use two tokens, this and that. Yeah, we have to get used to that. Two tokens are required when declaring pointers. If you want to feel more comfortable, you can associate that with this, and that'll be just the same thing. Okay, so two tokens are required to declare pointers. So once we declare int asterisk ptr equals 0, that simply means that we are declaring another variable called ptr. It will have its own memory address, like 1064 here, but it will store 0. Okay, so we have two entities. A num variable storing 10, starting address 1004. A pointer variable storing 0 because I put 0 here. If I didn't, it will be undefined. And starting address 1064. Pointers are usually 4 bytes. Could be 2 bytes depending on the operating system. Okay. All right. And pointers don't contain anything. If you put a 0, that means they just have a 0 value. Right now it's not pointing to anything. To point a pointer pointing to somewhere, we have to make a connection between a variable and a pointer. We're doing that in the next slide. If I do this, int num minus 10 is declared, which is this guy over here. ptr was declared, which was that guy here. But then I do this line here. ptr equal to address of num. Meaning of that is, hey pointer, copy address of num inside yourself. So this 1004 will be copied here. Okay. Can you see this? We saw in the Xcode that if you put asterisk in the front, then we can get a read and write access. Well, we can do that. We'll go back to Xcode and show you that in a second. But important thing to realize here is now pointer has a pointee. This is a pointee, this is a pointer. This is a pointer-pointee relationship. If that seems like a tongue twister, fine, but that's what it is. As soon as I make this assignment, this pointer will store this address, and although in RAM there is no line going like that, there is a connection between these two. Now I can access num through the pointer. Remember, I had put an asterisk in the front. I was able to print the value, this value. I can do that through the pointer also. I'll show that to you real quick. One more time. Pointer, pointee, pointer stores address of the pointee. Okay. Without pointees, pointers are useless. They have no purpose whatsoever. Okay. All right. So we can have read access to pointer through pointer, and all three of these will print -10. We showed in the Xcode this one and this one. Now we're going to show you this. Okay, let's go back to Xcode. Okay, so I can just do that right here. I can declare a int pointer, int asterisk ptr equal to 0. You don't have to do in two line, but if you do in two line, that's fine. And then I say ptr equal to address of num. Pointer, pointee. Now this contains the address of num, and I could print. So remember, I printed value of num this way. Then I printed address of num in hexadecimal. Value of num. Maybe I will move this temporarily on the top, so I can see all three values printing 10. So let me just take that out of here. Right, put that right here. And then print it through the pointer ptr. So that will be printf num value printed through its pointer ptr. You still need to provide a format string. That is simply this ptr. Meaning of that is, hey pointer, you have address stored inside you. Go to the pointee, grab that value, bring it. It was the same thing here. All these three lines will print -10. I'll show it to you. -10, -10, -10. First three outputs, -10. So this is read access through pointer. Over here I had shown you that you can change the value through this syntax, but now there is a simpler way to do that. Simpler way to do that is using pointer access. Okay, and that would be, let's say, ptr, put some value, let's say 33. Meaning of that is you have an address stored inside ptr. Go to that location whose address is here, change the value to 33. If I repeat these three statements, now all three will print 33. So you'll see -10 printed 3 times, -33 printed 3 times. Okay, let's run it. And there you go. -10 printed 3 times. We change the value to 33. -33 printed 3 times. Okay. If you're not convinced that ptr contains memory address of num, Well, let's print it. So we printed address of num through this syntax earlier using %p. Okay, I'm gonna move this up a little bit. Or actually, if you prefer this form, let's just use that. So that's through the address of num. Okay, so right here. And then we can also print through pointer, because pointer will contain this address. So let's make a copy of this, put that in here. I'm gonna remove this and put just PTR here. Okay. You'll notice that these two addresses, where I'm directly printing using ampersand sign on the variable and value stored in the pointer, would be same. That means this assignment copied address of this variable into this one. Otherwise, whole thing won't make sense. So after 10 is printed, minus 10 is printed 3 times, 33 is printed 3 times, we'll see these two addresses being the same. And you will see that minus 10 printed 3 times, 33 was, okay, fine. Yeah. You can see these two addresses in non-hex, one printed through address operator and one through what is stored inside the pointer. They're the same. Okay. That means when we use syntax like that, pointer will store address of the variable on the right hand side, and a pointer-pointee relationship is established. All right, and that's shown in this slide here as well. Okay, so now I'm saying I'm doing dereferencing on a pointer here. We want to clarify some of that. Dereferencing is not a double pointer. When we put asterisk in front of a pointer variable, meaning is this: follow the pointer to the address stored in the pointer or to the pointee, grab the value pointee, then do with that value what program statement directs you to do. Asterisk PTR is a dereferencing or follow the pointer, or indirectly reaching the memory location which is stored inside. Dereferencing is not a double pointer. Okay, as I said, in the Xcode we can get access to a variable whose address is stored inside the pointer. If I do this, num equal to minus 10, pointer got declared, pointer got address of num stored inside. We can print by dereferencing or indirecting the pointer to the console. Minus 10 will show up. Now I can actually change the value stored here, which was minus 10, if I do this syntax here. Asterisk PTR equal to 99. Meaning of this is follow the pointer to pointee wherever this variable's address is. Change the value stored to 99. And previous picture, okay, that may have been a long time ago, had minus 10, but when I do this syntax, asterisk PTR means go to the pointee at the address located here, change it to 99, and then this will happen. So in a way, asterisk PTR, once a pointer has a variable's address, asterisk PTR becomes alias or another name for that variable. Okay. This doesn't seem very useful right now because the variable is already declared, it has a name. You may ask, why are you giving another name? But it'll be more useful when we do talk about dynamic memory allocation through malloc, where variable created will not have a name. That'll be a little bit later, okay? Understand syntax of read-write access to pointer. Syntax of read-write access using pointer is very important. Putting asterisk in front of pointer makes it an alias for name of its pointee. Here I'm using C++, but it'll be, if you do printf, it'll be the same thing. If I do this, programming statements such as printf, format string, and comma, ptr, give read access to the pointee. And it'll, in this case, it'll print pointee value to console. But if you use program statements like this one, this gives write access to the pointee. It'll change the value stored in pointer to 99. There are alternate syntax of creating pointer variables. You could do it this way, asterisk attached to int, as if it's a new data type. You can put it in between, or you can attach that. Where you put asterisk is a matter of style. I usually put it in the middle. Okay. You could declare multiple pointer variables in one line. I prefer not to do that. If I have int asterisk ptr1, asterisk ptr2, asterisk ptr3, asterisk ptr4, these are all int type pointers. They can store variable addresses of int type up to 5. None of them are initialized, none of them have pointees. Uninitialized pointers are called dangling pointers. Pointers without pointee are called orphan pointers. You could mix pointer and non-pointer declaration in one line as well. Perhaps somewhat confusing to a student is a declaration like this one. Int asterisk num, asterisk ptr, then you have value, then you have asterisk iptr, then you have a variable called data. In this declaration, this asterisk does not apply to all. It only applies to num. Okay? So num, ptr, and iptr are pointers, but value and data are int type. Okay? So be very careful when you see multiple declarations like that. They're not all pointers. This and this, which has no asterisk, are the int type. All the ones that have asterisk, whether it's attached here or here, doesn't matter, are pointer type. Okay, pointer can only store address of type of pointee matching the data type in their declaration. Pointers that are declared as certain type are not free to store address of pointee of other types. There's only one pointer that can do that, void pointer. We won't talk about that right now. If I declare int asterisk ptr, it can only store address of int types. So below is a compile error. I declare a int type pointer, then I declare GPA double type 3.9, and I try to do this ptr equal to address of GPA. That's a compile error, POW, because it's not declared to store address of double type. It can only, it is very faithful. It doesn't do double duty. Int asterisk ptr is declared, then ptr can only store address of int type. Other non-matching type it can't. These are example of pointer to other types. Char asterisk cptr, pointer to a character, can store address of a character variable. Double asterisk dptr can store pointer to a double type. Float asterisk fptr can store address of a floating point type. If I define a student structure, student asterisk s2ptr can store address of a student structure union. This is a null pointer. All others that do not have 0 on the right are dangling pointers. All are orphan pointers. Do not dereference an orphan pointer that may crash your program. We'd like to show you a video about that, a Binky video. I'll do that in the class, Stanford video, what kind of program crashes can happen. For pointers to do something useful, it must be attached to a pointee. Pointers are totally useless if they are not attached to a pointee. So thus, orphan pointers should not be dereferenced. An attempt to dereference an orphan pointer may crash your program. Smart compilers will give some sort of warning. And in Xcode, it will not crash because it's a very smart compiler. But let's see if whatever it shows, it will. So let me see if I can do that. So I'll do that up front here. Hey, I'll just int asterisk x, and then I try to do something like this, that printf, %d /n, comma, dereference x. And I try to say value of x here. Okay, let's see what happens. I mean, I think Xcode is a very smart compiler. It probably won't crash the program, but I don't know. I'm trying to find out. See, build succeeded, and see what we got. Yeah, it says value of x is 0. That means Xcode, being a smart compiler, assigned this pointer to point to a 0 value that has 0. But a lot of other compilers will crash, or it would have undefined behavior. So pointers without pointee should not be dereferenced the way I have done in this line here. Okay, so we have been talking for a while. We really don't want to do much more than that in this video. Crux and summary is that pointers are usable to store address of variables. They can store address of functions and constants as well. And once we have done that, then we get a pointer-pointee relationship, which looks like this one. In the next video, I will show you how address to variables can be passed to the functions, and then we can manage that memory location, change it, print it, anything. I'll show that for the small blocks of memory first. For large blocks of memory, we'll have to wait until we learn something about arrays, although a character pointer character array can certainly be considered where I have stored large amount of text as a large block of memory. Okay, so I'll see you in video number 4 on user-defined functions. And we have learned enough about pointers now to show you how pointer data can be passed to the functions as another memory, as another parameter passing mechanism. Thank you.